Despite the recent popularity of additive manufacturing, such as 3D printing, subtractive manufacturing through CNC machining remains one of the dominant manufacturing processes for high-volume production of finished 3D products. In CNC machining, a cutter goes around a 3D material block to carve off a residual volume to produce a target 3D object. The most commonly applied subtractive manufacturing method uses 3-axis machining, where the cutter moves along 3 degrees of freedom. However, this task is quite involved. For example, consider how a freeform 3D shape with high genus, such as the fertility model, can be machined due to self-obstructions by the object's parts and physical limitation of the CNC machine, for example, cutter length. It is often not possible to completely carve a freeform 3D shape from a single direction. In practice, machining experts must plan the machining process by avoiding unnecessary shape setups on the operating table and repositioning the cutter on the shape, since each setup is an expensive and delicate process. Finding a minimum number of setup directions is highly challenging for humans, especially when the target 3D object is freeform and geometrically complex, such as the fertility. Moreover, finding a minimum number of directions is far from the only consideration. Here are 2 carving directions for the same object, but for the one on the left, the 3-axis machine cannot complete the carving in a single continuous path. The cutter needs to be stopped and repositioned many times. Hence, continuity of the carving is another criterion for efficient CNC machining, as shown on the right. In this paper, we introduce a fully automatic method which jointly optimizes the number of setup directions and the number of continuous carving paths to traverse the entire residual volume. A volumetric part is carvable if it can be fully traversed by the CNC cutter along a single continuous path. Geometrically, carvability combines visibility and monotonicity. It presents a new geometric property of shapes which had not been studied before. Our joint optimization problem can be formulated as a volume decomposition problem, which prioritizes minimizing the number of setup directions while striving for a minimum number of carvable volumes. We call the problem carvable volume decomposition, which is a hard combinatorial optimization problem. Hence, we develop a heuristic solution consisting of the following steps. Given a target object and a material block, we first sample the residual volume by a set of points, and sample a hypersphere by direction vectors. For each sample point, its accessibility via directions is analyzed considering the cutter's length. Then, to minimize the number of setups, a set cover is solved to find a minimum number of directions to access all the sample points. Among solutions of the set cover, we choose the one producing fewer number of shallow segments. Our key observation is that under a direction set resulting from the set cover, there are points that are only accessible through a single direction. We call them single access points, or SA points. We use SA points as seeds to grow candidate carvable volumes by simulating the movement of the CNC cutter. If necessary, sample points that are not covered by regions grown from the SA points are used to grow complementary volumes. Finally, we find the optimum order of carving these carvable volumes that produces the fewest number of shallow segments. For 3D objects, after obtaining the carvable volumes, we generate a toolpath for each volume by using Fermat's spirals to cover each layer. To validate the efficiency of our method, we tested whether it produces optimal results for simple 2D shapes with verifiable optimal solutions. In all the cases tested, our algorithm produced the optimal number of directions and carvable segments. We also compared two decomposition solutions provided by machining experts. Here are some comparison results. Now we show 3D decomposition results generated by our algorithm with some fabricated results. More results and details can be found in the paper. Thank you.